So now we're going to look at some properties that the derivative function holds, specifically, I guess, what differentiation holds. So differentiation is what's known in linear algebra as a linear map. And with those come some special properties. So these are properties that you see for a lot of different types of functions, including the derivative. We'll also see them for the integral, for example. So first is the sum rule. Okay. So this is that the derivative of f of x plus g of x. Okay. And for all of these, we're going to assume, by the way, that f of x and g of x are differentiable. Otherwise, this wouldn't make any sense. So the derivative of f of x plus g of x is the derivative of f of x plus the derivative of g of x. Okay. So we'll prove this first one. The rest of them are, pretty much the exact same in a proof. So we'll just prove this one. Okay. So the limit as h approaches 0 of f of x plus g of x. Okay, so this would be f of x plus h plus g of x plus h minus f of x plus g of x in parentheses, so f of x minus g of x. Okay. And what I meant by in parentheses was that it would be like this, right? Minusing that entire thing in here. So if we just go ahead and distribute that negative sign, then we'll get this over h. So one trick that we can do here, that's kind of common in these derivative proofs, is that we can regroup the terms. So this is the limit as h approaches 0, f of x plus h minus f of x plus g of x plus h minus g of x. Okay, we can group them like this. This is just the associative property of addition. And then we can break up this fraction into two fractions. And then we can break up the limit with them also. So this is f of x plus h minus f of x over h plus the limit as h approaches 0 of g of x plus h minus g of x all over h. And then the left one here is just the derivative of f of x, and the right one here is the derivative of g of x. Okay. So we have shown that the derivative of the sum is the sum of the derivatives. Okay. So perhaps unsurprisingly, you could just go ahead through this proof, change some of the pluses to minuses, and then not much is going to change here. So the difference rule, okay, difference rule, or let me put it to the side here, is that the derivative of the differences, f of x minus g of x, is equal to the difference of the derivatives. Okay. So we can break up that derivative over subtraction. And then the next one, the last one, is the constant multiple rule. Okay. So this says if k is a constant, so it's just some number, then the derivative of k times f of x equals k times the derivative of f of x. So in other words, you can pull a constant out. So this is useful just for things like, for example, if you take the derivative of 5x squared, you can take that 5 out, take the derivative of x squared, which is 2x, so you get 5 times 2x, which is 10x. Okay. Again, this is very straightforward from the definition of the limit. So, for these ones that I'm not showing, it's always good practice to go ahead and try to show them yourself. But if there's ever any questions about it, of course, you can let me know. Another one to keep in mind here, the derivative of a constant is always going to be 0. So I'm not going to say that's necessarily a rule. I guess we could say it's like an example. If k is a constant, then, and we usually use c for constant. So we like to use k if it's being multiplied by something, but we use c for constant a lot. So let's say if c is a constant, then the derivative of c is 0. Okay. And we can easily show this with the definition of the derivative. Limit as h approaches 0 of f of x plus h, which is c, minus f of x, which is c, right? There's no x in here, so everything is just c is h. So this is c minus c on the top. So this is the limit as h approaches 0 of 0, which is 0. Okay. So the derivative of any constant function is 0. Okay, so let's just do an example. This kind of combines what we're talking about in this video, but also one that we just haven't really seen an example of yet, which is finding the equation of a tangent line. So let's find the equation of the tangent line to f of x equals x squared minus 4x plus 6 at x equals 1. Okay, so again, we haven't really seen how to do this, but we have all the pieces. So hopefully, if you've already tried this, maybe you're able to figure something out here, kind of get an idea of what to do at least. Right, if we think about the tangent line, the equation for any line is y equals mx plus b. The m in this case is going to be f prime of 1. Right, because the slope of the tangent line and the derivative at that point are the same thing. And then we can easily find x and y. We already know x is, or we can find the f of x point when x equals 1, right? Namely, we can put in 1 for x, and we can put in f of 1 for y. Okay, and then we get this function right here. So in general, the tangent line of f at x equals a is f of a equals f prime of a times a plus b, where b is the y-intercept of the line. So usually if you have the function, you can find f of a, f prime of a, and then you can solve for b. Right? So let's go ahead and do that for this one. So first we'll need, we could look at different things first. We can do f of 1 first, for example. F of 1 is 1 squared minus 4 plus 6. So 1 minus 4 is negative 3 plus 6 is 3. And then f prime of x equals 2x minus 4. So here we're using the power rule, right? So the derivative of x squared is 2x. The derivative of minus 4x. So here we're, it's like minus 4 times the derivative of x, which is going to be 1. And then the derivative of 6 is a constant, so that's going to be 0. Okay, so now f prime of 1 equals negative 2. Okay, so the derivative of the tangent line then, the equation of the tangent line, you always write lines with the form y equals mx plus b. So we know m is negative 2. We can find an x and a y point, and then we can solve for b. So that's really what this equation is here for, is for solving for b. You wouldn't generally put a and f of a in there. You wouldn't put like a specific point in there like that. So we have 3 equals negative 2 times 1 plus b. So b is going to be equal to 5. Okay, so the tangent line is going to be y equals negative 2x plus 5. Okay, so we had to use the power rule for all of these. We also were using the difference rule and the sum rule, which I didn't mention, right, to find the derivatives here, because we just took the derivative of each part of this individually. So these are really powerful rules that will really simplify how we can take the derivatives by breaking it up into taking the derivatives of each individual part.